today, Mark will be giving a talk today this morning on graphlet sampling. So without further ado, Mark Bressan.
Thank you. Thank you, everybody. Thank you, the organizer, for the invitation, for the ibuprofen, and for switching the talks. So this talk is about subgraph sampling. And if you are into subgraph counting, this will almost be your stuff. And so the flavor is algorithmic combinatorial sampling, rejection sampling. There will be no black box exotic results used here. It's all like from basic ingredients. Part of this is existing results in the sense that results by me a couple of years ago, and then some recent follow-ups with these other authors. Okay, so the problem is as follows. You are given a simple graph G. Think of it as of a very large graph, social network, typical example, and an integer. And the problem is to output a uniform random connected subgraph of G on k vertices. Okay, so for k equal 3, this will be either a clique, so a triangle, or a wedge, and then you get for higher sizes. Typical application is mining networks to estimate the relative frequencies of all connected k-vertex induced subgraphs. So the relative ratio of, let's say, cliques and cycles and paths and so on and so forth. And this has been brought, let's say, to fame, if I can say so, but by several people who did bioinformatics, because they discovered that the frequency spectrum of these graphlets, these connected k-vertex subgraphs, gives a lot of information about biological networks. For instance, in protein-to-protein interaction networks and this kind of stuff. Okay, so when I started getting interested into this problem, there was a lot of work already done by these people, and then this transferred to the applied community, KDD, Wisdom, these kind of venues, and everybody was looking for a method to sample efficiently, because of course, if you can sample efficiently, you can estimate this frequency distribution, right? And there were a lot of nice works, but all of them had some fundamental limitations. And so many of them, for instance, work only for small values of k. By small, I mean really only for 3, 4, or 5. And they really break if you try to. It's not even clear how the method should be defined for k equals 6 or larger. If they can be extended, then many of them, in the worst case, give n to the theta of k time per sample, which is like you can do that brute force, of course, and brute force time. So that's not interesting. Or if they gave a better running time, then they yielded samples that are far from being uniform. Okay. So the situation was a bit confused. It was not clear what the actual complexity of the problem even should be. Or could be, right? And so I got into this problem, and I'll tell you directly what are the results. And the two results that I proved some years ago are these two. So two algorithms, which I call the linear one and the sublinear one. The first one says that there exists an algorithm that returns exactly uniform subgraphs, so k-graphs from the graph. So samples that are perfectly uniformly distributed with no approximation. It is a two-phase algorithm. It has a preprocessing and a sampling. Then preprocessing runs in basically in linear time in the size of the graph. And after the preprocessing, you are guaranteed that every sample you take will be, as I said, uniform from all connected k-vertex subgraphs of G, and the expected time to get a sample is only logarithmic. And the second result is, let's say, stronger in some sense. It says that if you allow for non-uniform samples, you want epsilon uniform, so that means that you want only to get in total variation distance epsilon close to uniform, then it is sufficient to have a preprocessing time that is n log n. So for mildly dense graphs, that means you are not even looking at all the edges of the graph. Okay. And then you get a constant sampling time. By constant, I mean it's independent of n. It depends only on epsilon and on k. The dependence on k is like bad in both cases, but there are good reasons to believe that you cannot avoid that. Yeah, you know this probably. And so these are. Both of them are in some sense surprising. The first one in particular has a surprisingly simple solution once you see it. Once they tell you what is the preprocessing phase, you do some computations and everything falls into place, and you discover that the sampling phase can be done in this and yields perfectly uniform samples. And the second one is surprisingly harder to prove than the first one. And okay, in most of the talk, now the rest of the talk, I will give you an idea of how this works. And this, as I said, is like a couple of ingredients carefully put into place. The second one is harder to explain. There is no clean, nice reduction to some other problem. It's a set of ingredients interwoven in a complicated way. So we try to give an intuition, but I myself could not find a simpler and better way to do it. It's the proof is a mess. Okay, that's the thing. And then we have some ongoing work importing these algorithms to streaming and MPC models. Okay, so let me start with the first algorithm, the linear one. So uniform sampling with linear preprocessing. And as a starting point, let me use rejection sampling. So we will use a two-stage sampling where, yes? Of the output graphlets. Yes. Right, yes. It's, if you consider all the k-vertex connected induced subgraphs of G, so all subsets of the vertex set of G of size of cardinality k, such that the induced subgraph is connected, this will be your family. You are uniform over that. Okay, so the output is, if you want a subset of k vertices of G, and you're guaranteed that the subgraph induced by those is connected. Let me say, what is the model of computation here? I forgot. Okay, standard RAM model with logarithmic word size, and the graph is given as adjacency lists. Okay, so you have all edges of vertex 1, all edges of vertex 2 in arbitrary order, and so on and so forth. Okay, to start with, we use a two-stage sampling. What does that mean? First, we pick a starting vertex v with some probability p of v, and we will see what that is. And then we just grow a random graphlet around v. Okay, for that purpose, we just look at sampling, which means we look at the edges incident to the current subset we have in hand, and we pick an edge uniformly at random, and so on and so forth. And when we have collected k vertices, at this point, we compute explicitly the probability that this process yields exactly what we have obtained. Right? We can do that. We have all the information to do that. And then at this point, we perform a rejection step, which just means, suppose that we know the smallest non-zero probability to obtain of any graphlet returned by this process. And let me call that P star. And then if I have sampled S, I just accept it with this probability. Okay, this is just standard rejection sampling, not imaging here. Yes?
Are you assuming that there is preprocessing also so that every node knows all its edges, its neighbors?
I know that because the input is given in adjacency list. So I have V, I can access its adjacency list, and I can see that.
So it's not just given as an arbitrary list of edges.
No, they are collected by endpoint. Yeah. And but in this case, it will work even if I had an arbitrary, because in any case, in linear time, I can of course collect them, so it will work in any case. that won't ruin the running time. Okay, and then if you just do the calculations, okay, what is the probability that a specific subset S is returned? Well, the probability that it is sampled by this process up to here, which is exactly this, and then by construction, I am accepting that with this probability, otherwise I'm repeating the process. And the result is not a function of S, so this means that the samples are independent, are uniform, great. And the price to pay, of course, is that now the acceptance probability, which is this one, can be very, very, very small, okay? Because you have basically no control. It is not clear how these two terms behave like with respect to this one. So this P star might be very, very small compared to the denominator, in which case, here you are accepting with very small probability. This means you could have to do a lot of rounds before accepting one graphlet. So your sampling time blows up. Okay. So our goal now is to fix this. Uniformity is granted by rejection sampling. We are going to fix the running time. Okay, so this is the problem, and what we are going to do is we will make the sampling distribution almost uniform. That is, we will ensure that for any two graphlets will be sampled with roughly the same probability by this process of picking V and growing the graphlet. Whereby almost the same, I mean that there will be a distortion by a factor only k to the minus order of k. Think of it as 1 over k factorial, if you like. That's roughly the truth. Okay, and this will make the rejection probability large, so only a function of k of this. Okay, and everything will be efficient. Okay, so here is the preprocessing that makes everything work magically. Okay. We compute a total order over the vertex set by repeatedly removing a vertex of maximum degree. Okay, so it's like the core ordering of a graph, but just the inverse rule. And this takes linear time by standard bucketing algorithms. And now let's look at, so this is the ordering. Let's look at a vertex V and all vertices after it in the ordering. And I call the corresponding induced subgraph G of V. And I call B of V the set of graphlets that contain V and are inside GV. Okay, so any graphlet that is, let's say, anchored to V and then is around here. And for every vertex U here, let me define du given V as the degree of U in G of V. So the degree of U given V here will be 3, even if U has edges to other vertices around there. Okay. And now here's the first crucial observation, that thanks to this ordering, if there are graphlets in GV, so the bucket BV is non-empty, then the size of the bucket, so the number of graphlets in it, is roughly the degree of V in GV to the power of k minus 1 by a counting argument. And why is that? Because V is, by construction, the largest degree in this subgraph. So if I start growing a graphlet from here, so any graphlet that contains V and is in GV can be obtained just by exploring starting from V. And at every time, the number of edges I can select is bounded by the number of edges incident to V here, union those of the other vertices, but those have degrees smaller than V, not larger than V. So, and so this gives us the first ingredient. We will pick V as a starting point for our sampling process with probability roughly proportional exactly to its degree in GV to the power of k minus 1. Okay, and this means we are choosing the bucket with probability roughly proportional to its size. And so this is for choosing V, and then the other two observations are that now if we run the cut sampling process, I told you before, start from V and add edges, but limited only to GV, so we look only at edges in GV. Then every graphlet lying in GV anchored to V is sampled with roughly the same probability by basically the same counting argument I just used. Okay. So this kind of regularizes the graph if you want. And then if you multiply the two probabilities, now you get roughly uniform distribution. Okay. So just sorting the graph in this way gives you for free an almost uniform distribution. And last observation is that we can make all of these efficient. All this process of growing the graphlet and computing the probability, blah, 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 can be made efficient. And why is that? Because all I need inside here is to access the edges of any vertex I encounter that are inside G of V. And what are those? Well, if we sort the adjacency list of G by the same total order that we have here, the edges of U in GV are just the suffix of the adjacency list of U, the suffix starting at V. So I just need to do a binary search to locate V in U's adjacency list. And that gives me the starting point of the sub-adjacency list that contains all edges in GV. And with that, I can then sample, do whatever I want. So that's where the log n in the sampling comes from. Okay, so to summarize, this is how the algorithm looks like. You just compute this total order and compute your estimate of the bucket sizes, as I told you. There is only one additional thing, that is you have to check if buckets are empty, because you might discover that only a sampling time, then you have to stop and retry with another bucket. That could happen up to n times for n different buckets, but that's not going to add much running time. So the total order is linear time. This is, of course, of n, we're just computing n integers. This thing adds just a factor k square log k via truncated BFS. And then this is the sampling part with the log n due to locating the edges in the subgraph GV and so on and so forth. There is a small blow up here in the computing the probability for the rejection, because you have to take your graphlet S and consider all possible ways in which it could have been obtained by S, so all possible orders in which the nodes of S could be chosen. And so this gives you a k factorial, basically, okay? But nothing worse than that. So if you sum up, you get the guarantees that, that I was talking before. Okay, and this was the linear algorithm, and now the hard part is actually the sublinear one. So I'm only gonna sketch it, of course. And okay, the starting point is what follows. Let's try to decrease the running time of the preprocessing. That's our goal, right? The primary goal is to decrease the running time of the preprocessing. And so the key property that we used in the linear algorithm was that V had the largest degree in the subgraph GV. That's what ensured that everything worked. Now let's try to relax this assumption, because the idea is that if I don't look at all the edges, but maybe I only sample edges, I can still ensure this property approximately, you know. And then, for instance, I can be happy if V has approximately the largest degree in GV, so it has at least alpha times the degree of any other vertex in GV, maybe 1/2 or whatever it is. And then we just lose this factor of alpha later in the sampling. But maybe I can obtain this efficiently, you know, by just sampling a couple of edges and estimating, running a sketched preprocessing. So the naive attempt would be like compute like an epsilon, let's say, what I call an epsilon degree dominating order, this one, in this time, just making a guess, and then just sample as before. And the thing is, this doesn't work. And I couldn't find any way. I found good reasons for which this cannot work. And what I came up with was a much more complicated condition. So I relaxed this notion of degree dominating order into this ugly 4 points condition. Okay, and it is complicated because it is the result of several interaction of back and forth between, let's try to find a sufficient condition for the sampling. Oh no, but now I cannot satisfy it in a good preprocessing time. Okay, let's try to find a weaker condition that I can, you know, ensure in. And I kind of settled on this. So let me try to parse this out. Okay, now we are not only requiring an ordering, but we want a total order, so an ordering, so a total order or V, and a set of numbers that are estimates for the bucket sizes. Before we use the degree to the k-1, now they are going to be something else. And the conditions I want is, okay, if I believe, so the estimate tells me that the bucket is non-empty, then V has, okay, this would be D of V given V. Sorry, this is a G of V, but take it as given V. So the degree of V in GV is at least alpha times the degree of U in GV, plus some other technical condition. Okay, so this is just the relaxation I was talking one slide before. The second is if the bucket is believed to be non-empty, then the estimate itself is a good estimate of the bucket size. I'm losing a factor of beta, but otherwise it's, it's close to the actual bucket size. And third, the buckets that I believe to be empty, according to these estimates, contain only a fraction at most beta of all the graphlets. So if I ignore those, I'm not losing much. I'm discarding a small fraction, so if I can sample uniformly from the other buckets, I can still get close to the uniform distribution. Then there is this weird technical condition that I will not explain. And now the magic is I can prove that in time this I can compute with high probability such an object. Okay, so this weird relaxation of the degree dominating ordering for a certain value of alpha fraction of beta, okay, for which I don't have good intuition. And I give you just a sketch of the algorithm and the proof. I was tempted to give you a proof by overwhelming, by drawing the graph of dependencies between the observations of the lemma, but I got overwhelmed myself and I gave up. But the idea is that I start with a candidate total order, which is just the ordering by the degrees of the vertices. Okay, so I take the vertices in non-increasing order of their degrees, and then I say, okay, maybe this is the right order. Let me test it. So I take every vertex in turn, and I sample roughly log n random neighbors of it from its adjacency list. Okay. And then I see how many of these neighbors I discover that are after the vertex in the current total order. If there are many such neighbors, okay, then I say, okay, then the degree of this vertex in the original graph is not so far from its degree in this subgraph, right? So I leave it where it is, and I use its actually degree in the whole graph as a proxy for the size of the bucket. That would be inapproximate, but only to factors that are a function of these things here, beta, k, and so on and so forth. Otherwise, if I see too few neighbors to the right of the vertex, I say, no, this is not in the right place. I push it to the end of the ordering. Okay, because that is, the intuition is that this should not be its place. There will be some other vertex that has a largest degree in this subgraph, a larger degree in this subgraph. Okay, so now the idea is we use this to compute this alpha epsilon degree dominating order in this magic time. Then comes the sampling phase, which is again not for free. And the thing is, okay, if we could run the original sampling phase, okay, of the uniform algorithm, that just performs rejection sampling and ensures uniformity of the samples by construction. And since by the third property of this object, we know that the buckets whose estimates are greater than 0 contain at least 1 minus beta, in overall, at least 1 minus beta fraction of all graphlets. If I set beta to be epsilon, the sampling phase will sample from a population that is, all graphlets minus a beta fraction. It will be uniform over that, so I will have achieved my beta uniformity or epsilon uniformity. Beautiful, but this doesn't work. I mean, it works, but it is extremely inefficient. Why? Because we don't have the sorted adjacency lists anymore, because we can't sort them in this time. And so when we do the cut sampling process to grow the graphlet, even to locate just one edge in the adjacency list of the vertices, we might need time big omega of n, because there might be only one edge in the cut, and in the cut of the current subgraph we are looking at, hidden in all other vertices, all other edges, right? Before we could do that efficiently because we could locate precisely the subset of edges in the cut by binary search. Here we can't. Okay, so the goal now is to reduce these to big O of 1. And I will give you just an idea, so it's just one slide. And the idea now is to relax the conditions slightly. So to tighten the preprocessing condition slightly in the following way, we set the beta to epsilon over 2, and that means, again, by condition 3, that we are preserving fraction 1 minus epsilon over 2 of all graphlets. So now, if we achieve epsilon over 2 uniformity over the buckets with positive size estimates by triangle inequality over the total variation distance, we will be epsilon uniform overall. Okay, so now our goal, once we have done this and computed our alpha beta magic degree dominating order, the task becomes sample epsilon over 2 uniformly from all the buckets, from the union of all the buckets that have positive size estimates. And then it turns out that we can do that efficiently. So first, the first ingredient is, okay, how do we grow? Let's say we choose a vertex V with probability proportional to its bucket size estimate. And now we have to grow our random graphlet in it. How do we do that without the sorted adjacency lists? Well, we estimate the cut. And to do this, we couple this. This is why there are these technical conditions here. It's not so easy to grasp at first sight, but basically what it says is that this condition in the middle here and this down here tell you that the degree of V is not much larger than its degree in the subgraph. And the degree of every U after V is also not so large. And this puts a bound basically on the size of the union of the adjacency lists that you have to look at to find a vertex in the cut. And so by sampling, this ensures that you can find one edge in the cut and grow your graphlet with a decent number of samples, not too many. Again, this will be a function of this beta, alpha, and k, but it will not be a function of n. We're independent of n. And so we can run the growing process with estimated cut sizes. Okay, so I will choose edges from the cut almost uniformly at random, and this will give me graphlets that are sampled almost uniformly over the buckets. Once I've chosen the bucket, it will be almost uniform. The same I will do for computing the probability after I have obtained my graphlet. And once I have done all of these, it will be all approximate, but still the approximation is not a factor of n. And finally, by condition 2, I will know that if I plug it in as I did before with the calculation to show that in the end we get a uniform distribution, and the acceptance probability will be only a factor of k, this also will give us an acceptance probability that is also only a factor of k and again of this guy. So the algorithm looks just like a uniform one, only with now this computing this magic object instead of the exact ordering. The probability of choosing a bucket is now proportional to its estimate, and this is the thing, the sampling thing I just talked about. And it's all fine. You only have to lower somewhat the acceptance probability to make sure it is in 0, 1. And these add some other poly epsilon minus 1 factors, but overall you get this sampling, expected sampling time. Okay, I just want to mention quickly two extensions we are working on. These are extensions of the linear, so the uniform sampling algorithm for streaming and massive parallel computation. So in streaming we have what follows. We assume, so this is the semi-streaming model. We assume a memory of n log n words of logarithmic size, and G is arriving as an arbitrary stream of edges. We do the preprocessing and sampling exactly as we did here, only that now the preprocessing is taking log n passes and this running time, and the sampling 2k passes, but it's going to sample a lot of uniform samples in parallel. So basically, all memory you have is filled with uniform, independent graphlet samples, and similar guarantees for MPC. So the two interesting ingredients here are that even though the preprocessing phase before was like inherently sequential, now you can do it like in peeling phases. Similar things done for other orderings, like a core ordering. Is not exactly the same, but the spirit is similar. And that you can do in linear time, you can sample a lot of uniform graphlets in parallel. Okay, these are the two interesting ingredients. Okay, let me conclude with two open problems. And the first one is, what can we achieve without preprocessing? So here we are paying, it's an efficient preprocessing, it's linear time, but the question is, if I don't want any preprocessing, can I get something in between? So here we get linear preprocessing, log n sampling time, or even sublinear preprocessing and constant sampling time. Can I get anything in between if I don't want to preprocess? And the second one is, what about hypergraphs? Because it seems now that hypergraphs are the next thing in line for all this subgraph counting, because there's a lot for subgraph counting, a lot is known, but for hypergraphs, it's almost, I won't say almost nothing, but it's close to almost nothing is known. Thank you.
Can your method handle more constrained graphlets? Like, let's say you want graphlets of size k that are also trees only.
Right. If you want them non-induced, yes. If you want induced, that's gonna be harder. I didn't think much about this. You can do that, but then, you know, I don't know, because of course the natural thing is see what you get and eventually reject it. To me, this seems like quite fragile with respect to adding constraints, because very quickly you can get to things that are hard. The trivial example would be, what if I can choose what to sample? Give me a random click. Of course, that's hard. Obviously, okay. For trees, that might not be the case, but you know, boundary is there.
I had also a question. Is it clear that we need linear NM time to get epsilon uniform? So suppose you just want to get one sample.
Yes.
And then you get n log n time.
Yes. Okay. Yeah. Consider the following graph. You have it's a union of stars. All of them have k-1 vertices, except one. So just to find the one that has. So there is no k-graphlet except for the only one. Right. So if you assume that G is connected, then it's not clear. So under further assumptions, there might be faster algorithms.
Any other questions for Marco? If not, let's talk about it.
Thank you.